All right, so the focus of this video is on examining the bigger Lego workshop linear program in a little more detail. In particular, what we're looking at is how much more would you pay to obtain new resources or more resources than what you currently have available. So we have three separate and independent opportunities that have arisen that will allow us to get some more resources. So basically have a friend willing to give us an extra small brick a week, and we want to figure out how much we should pay that friend for that small brick. Our parents are willing to offer us 2 big bricks, and we want to figure out how much should we pay, or how much should we pay per big brick. And then we want to figure out how much more should we pay if we're able to increase the number of teas we can sell. So basically increase that T upper bound from 40 and beyond. And so what we're going to do in this video is talk about the concept of shadow prices, and then how shadow prices help us answer these questions, and then also how can we go about obtaining shadow prices. So the first thing we're going to look at is I'm just going to kind of focus in on kind of a set of slides for this example, and all we're doing is we're looking at the linear programming formulation in the bigger Lego workshop example that we've done and worked with in previous videos. So a couple things to point out. One thing is we obtained the optimal solution, and we know that the optimal solution was x1 is equal to 40, so we're going to produce 40 t's. x2 is equal to 0 means we're producing 0 cakes, and then x3 is equal to 80, we're going to produce 80 eyes. Now, one of our first questions was how much would we pay a friend if they're willing to give us an extra small brick? Well, the very top constraint is the small brick constraint. And one thing we can figure out is how many small bricks are we currently using with our optimal solution? Well, with our optimal solution, we're using 160 small bricks, 80 of those dedicated to T's and 80 of those dedicated to I's. So basically what we have is we have 40 small bricks just laying around our workshop at the end of the week. So question now becomes is how much are we going to be willing to pay to get that extra one from our friend? What will we do? Maybe another question we could ask ourselves is what will we do with an extra small brick? We're currently not using 40 small bricks. So basically what we would do is we get that extra small brick and then throw it in our pile of 40, so we have 41 laying around. We make no extra money, so why would we pay anything for that small brick? So we've kind of already answered the first question. Small bricks, we're not going to pay anything to get more small bricks because we're not using any more of them. So kind of 1 out of 3 questions away. But what we're going to work through with that small brick discussion and example in our head is we're going to make a connection between this concept of shadow prices and then the reduced cost of slack variables. So we'll get to the reduced cost of slack variables in a second, but we're going to introduce this concept of what's called the shadow price. And essentially a shadow price is how much is the optimal objective function going to change if we obtain more of one particular resource. Now, one thing I want to emphasize is this slightly that's italicized. We're only going to slightly increase the amount of resource available. And the reason why we're only going to slightly increase the amount available is that shadow prices typically operate under the assumption that the current optimal solution, current basic feasible solution that's optimal, remains optimal. So that's why we're only going to focus on slightly increasing. So I already just kind of mentioned optimal basic feasible solution, which means I'm going into the realm of the simplex method and finding the optimal solution via the simplex method. And if we go back to our original LP formulation of the workshop example, it's not in augmented form. It doesn't have equality constraints. Simplex method cannot be directly applied to this problem. So in order to start dealing with the simplex method, we need to augment that linear program. So all we're going to do here, we're going to add in slack variables so that all of the constraints become equalities. So we have x4, x5, x6 are respectively the small brick constraint, are the slack variables for small bricks, big bricks, and then the t upper bound constraints. And we already know the optimal solution, so we can augment it with how much and what the values of the slack variables are. So basically what happens is we use up all of the big bricks, we use up all the t constraints, so those slack variables x5 and x6 become 0. x4 we've already identified, we had 40 small bricks laying around. So x4 is equal to 40. Now what becomes a little bit interesting here is, well, if I look at that augmented optimal solution, turns out that it's a basic feasible solution. x4 is positive, which implies that x4 is a basic variable. And one thing we know about basic variables in a basic feasible solution is they have a reduced cost of 0. So x4 has a reduced cost of 0, its shadow price is 0. And it's not a coincidence that shadow price matches up with the reduced cost. And what we're going to actually do is we're going to actually establish a relationship now, or talk about the more general relationship, that if I look at the reduced cost of a slack variable associated with constraint, that actually gives me the shadow price for the resource associated with that constraint. So what we're going to do is kind of just show the final tabular form of that optimal basic feasible solution that we've determined, where again x1 is equal to 40, x3 is equal to 80, x4 is equal to 40, and then x2, x5, x6 are basic non-basic variables, so they're all values are equal to 0. One thing I want to point out, kind of good to point this out from a learning perspective, is that we have a non-basic variable in x2 that has a 0 reduced cost. So it actually turns out that there are multiple optimal solutions to this Lego workshop example. Basically what we can do is we can pivot x2 into the basis and figure out another optimal solution. One thing just as a reminder, basic feasible, or one thing as a definition perspective, remember that the reduced cost of variable is the rate of decrease in the objective function value as we increase the value of that variable. So the fact that we have a 2 in x5's objective function, in the row, objective function row in x5's column, basically means that if I increase x5 by 1, my objective function is going to decrease by 2. And it actually holds for all of x5's column. So if I look at the row with x4 as a basic variable and look at x5's column, that negative entry basically indicates that if I start increasing x5, I'm going to decrease x4 at a rate of minus 0.5, which means what really is happening is I'm increasing x4. So we're going to use this to start kind of establishing a relationship when we start looking at the second question associated with our resources. And the second question was basically, your parents are willing to give you 2 extra big bricks a week. How much would you pay for them? So let's look at that question. Suppose we can get 2 more big bricks. Okay, what are we going to do with 2 more big bricks? Well, one thing we can do, and actually turns out the best thing that we can do, is we take those 2 big bricks and make another I, right? 2 big bricks plus one of the 40 small bricks laying around will make an I for us. So we get $4 in return using those 2 big bricks to make a I, which actually means that the return per big brick was $2. And what we end up seeing is that if I got 2 more big bricks, essentially the right-hand side of the big brick constraint is, instead of being 200, it's 202. And it turns out that we can vary our basic variables, keeping that optimal basic feasible solution the same, but changing the values of the variables in it that are basic, is that x1 remains at 40, x3 now increases by 1 to 81, and x4 decreases by 1 to 39. So what actually happens is that we can find all of this kind of information about the changes to the variables in the final basic feasible solution. So let's look at this again. I mean, essentially what we said is that if I obtain 2 more big bricks, what is happening is that my objective function increases by 4. My number of i's increase by 1, and my number of leftover small bricks decrease by 1. Well, let's look at what's happening here. Well, this entire column for x5 corresponds to what will happen if we start increasing x5. Well, basically what we're saying is if we increase x5 by 1, we decrease the objective function by 2, we quote unquote decrease x4 by minus 0.5, so really we're increasing x4 by 0.5. And then x3 decreases by 0.5, assuming we make a change of 1 to x5. Well, really what happens if we introduce 2 new bricks, temporarily x5, 2 new big bricks, temporarily x5 gets driven up to be 2, and we need to drive it back down. We need to decrease x5. So if we're decreasing x5, everything in x5's column now represent the increase to the appropriate basic variables. So the fact that I'm decreasing x5, I'm really increasing the objective by 2. If I'm decreasing x5, I end up decreasing x4 at a rate of 0.5 for every one increase in x5. And then for x3, I'm increasing x3 by 0.5 for every unit increase of, every unit decrease of x5. So what we really have is we have all the information we need to know and the impacts on, we have all the information we need to determine the impact of increasing the set of available resources for x5 within the final form of our basic feasible solution, our optimal basic feasible solution. So what happens is that I can figure out the shadow price for the x5, for the big bricks, by simply looking at the reduced cost of the slack variable associated with the big brick constraint. In this case, it's x5. The same thing happens for x6. Basically, if I were to increase my t demand, so the right-hand side of the last constraint, by 1, x6 will temporarily become increased by 1. I'm going to have to decrease that in order, and by increasing my basic variables. So if I decrease x6 by 1, my objective function is increasing by a rate of 1 per unit. So ultimately, we've kind of discussed the intuition where if I have a maximization linear program with less than or equal to constraints, we have that the shadow price of a resource is equal to the reduced cost of the slack variable associated with that resource within the optimal final basic feasible solution. And it actually also turns out, if you've watched the duality video associated with the bigger Lego workshop example, that the optimal dual variables for the 3 constraints are y1 was equal to 0, y2 was equal to 2, y3 is equal to 1, which is exactly the reduced costs of the slack variables associated with each of those constraints. So it actually turns out also that the shadow price of a resource is equal to the optimal dual value of the variable associated with its constraint as well. So we have kind of 3 things that are all equal to one another for these maximization linear programs with less than or equal to constraints. Shadow price is equal to the reduced cost of the slack variable associated with that resource, assuming you solve it via the simplex method and the augmented in its augmented form. And then also if you just take the dual of the linear program, solve that, the shadow prices are equal to each of the optimal dual values of the respective variables. So that was just a quick rundown of the relationship of how to get, so actually, the shadow prices actually answer all these questions, right? If I know how much my objective function is going to increase, that gives me kind of an upper bound to how much I'd be willing to pay to obtain one more of a new resource. So that kind of ends our discussion on the shadow prices.